Hey, this is Mr. Ayton. Welcome back to Pre-AP Chemistry. We are in Unit 5, which is Intermolecular Forces. This is Week 8, and what are we going to take a look at in Week 8? We're going to be taking a look at physical changes as opposed to chemical changes. That Intermolecular Forces is all about physical changes. We're going to be taking a look at particulate models, covalent network, metallic ionic covalent, some of these intermolecular forces that we're going to experience as we go along. So let's start off with physical changes. A physical change is different than a chemical change in that a physical change is just breaking or forming intermolecular forces of attractions. Inter means between, so intermolecular means between molecules. So these are attractions. Chemical changes are breaking and forming actual bonds, but physical changes are breaking and forming attractions, which means we haven't really changed the molecule at all, or the substance. You can see water on the left-hand side is a solid, and you can see as a liquid, we have to break those attractions. And then water becomes a gas, which means we have to break more of those attractions. So we're changing the states of matter, and that's called a physical change. Is not the breaking of bonds. We're not changing the substance itself. It's still H2O. We are simply breaking or forming intermolecular forces of attractions, okay? And let's start off with our strongest intermolecular force. Our strongest intermolecular force is a covalent network solid. A covalent network solid. These are atom particles. They're covalently bonded in a network, which makes them very, very, very hard, very high melting points. Okay? It doesn't mean that they can't be brittle. It just simply means that they're very hard with very high melting points. These covalent network solids are poor conductors of heat and electricity. Some great examples are diamond, graphite. These are called allotropes of carbons. Things like silicon dioxide, which is called quartz. You can see the structure of diamond and graphite. They're different structures, same substance. They are covalently network solids as they're bonded together. And so it takes a lot of energy in order to break these attractions. These are very, very hard substances, but they are very poor conductors of heat and electricity. The next strongest is metallic, and metallic are atom particles as well, but they have what's called delocalized electrons. Their electrons are not in one place, but they are in a sea of electrons. And so there's a lattice of nuclei, a lattice of positive nuclei, but the electrons are scattered throughout, which allows metallic solids to become great conductors of heat and electricity. And you can see, which also gives you high melting points. It makes metals able to be malleable, ductile. Malleable means bendable. Ductile means you're able to make them into wires. And so you can see a pure metal just looks like atoms with a sea of electrons. We do have different kinds of alloys, which means mixtures of metals. You can see an interstitial alloy would be something like steel, where we have carbon atoms, which are very, very, very small in atomic radii, and we have iron right here. So iron has a much larger atomic radii, and the carbon fits in these little spots, which makes steel much stronger than just regular iron here because those carbon atoms fill in. We call that an interstitial alloy. We also have what's called a substitutional alloy. A substitutional alloy, this is when we take something like iron atoms here, and we mix it with something like cobalt, something that is very similar in its size, and you can see that's called an alloy, and those are called substitutional alloys. Things like brass would be a substitutional alloy, steel would be an interstitial alloy, and you can see those are metallic intermolecular forces. Then we have ionic intermolecular forces. We've covered ionic compounds before, and ionic is an intermolecular force. It's a fixed lattice of cations and anions, positive and negative. They're electrically neutral. These are poor conductors of heat and electricity as a solid, very, very brittle as a solid. But poor conductors of heat and electricity, how would we make an ionic solid become a great conductor of heat and electricity? Well, we need the positives and negatives to be free, to be delocalized, to be moving. And so you can either take that ionic solid and dissolve it in a liquid, which means make an aqueous solution, or we can melt it down to make it into a liquid. Now the positive negative cations and anions, the ions are free to move, and therefore it would conduct heat and electricity. These have high melting points because they are electrostatically attracted together in an ionic compound. And then our weakest of our intermolecular forces are the covalent or molecular solids, liquids, and gases. These are all three different substances. You can see we can have just atoms themselves, we can have large molecules, we can have smaller molecules, we can have diatomic gases. These are relatively low melting points, poor conductors of heat and electricity, and they are held together by polar and nonpolar attractions. And the next video, we're going to go more in depth onto this covalent or molecular intermolecular forces. But for right now, those are our four main types of intermolecular forces. They are covalent network, metallic, ionic, and what we call molecular there. And that is Unit 5, Intermolecular Forces, Week 8, Pre-AP Chemistry. Thanks for tuning in. I'll see you later. Bye.